Okay, let's start. So, good evening, good afternoon, good morning from wherever, whichever part of the world you are joining from. Thanks for joining this webinar series. Today is the first session of the series. So we are going to run, it's a three-part series for every week. Wednesday, there will be a webinar. So we'll be covering three topics under this series of virtual flow loop tests with Autonomous Valve CFD. So the first session will be focusing on valve flow coefficient, CV, and flow characteristics, how the trim design impacts the flow characteristics using CFD. And the next week we'll have hydrodynamic torque coefficient related session. And in the fourth consecutive week, like third week, we'll have cavitation index prediction. Okay, so let's go into this session. So I'll introduce the speakers myself. So my name is Praveen. I'm currently I'm the product marketing manager in Simulation Hub, and I have over 15 plus years of experience in CFD simulation applied to various fields, including valves and building HVAC and etc. And recently I did my PG course in product management from IIM Indore. Basically, I'm a mechanical engineer, and then I upskilled into product field, and then moved into product management and marketing related stuff. So with me, I have Akshay. Akshay is our young leader, budding leader, and is playing the role of business manager in specifically under simulation of specifically autonomous valve CFD. Akshay, would you like to introduce a brief yourself?
Yes, thank you, Praveen. So I'm Akshay. I've just recently got this role of business manager for AVC. I have a couple of years of experience in CFD. I have a master's degree in mechanical engineering, and this new role is quite exciting for me. It's making me get in touch with industry experts and getting to learn the business of AVC. So it's very exciting for me.
Yes, thanks, Akshay. Moving forward, this is the outline of today's session. So we'll start with a basic understanding of what is valve flow coefficient, CV. We'll introduce CV and how to calculate valve flow coefficient using three different methods like experimental, analytical, and the CFD numerical method. And what are the plus and minus pros and cons of each method. And then we'll introduce our autonomous valve CFD and we'll show how we can, using the AVC, Autonomous Valve CFD app, extract CV curves and other associated, flow simulation results. So that we'll give a demonstration. And we'll have a detailed look at a case study, which we brought specially for this session. So we have picked a globe valve design and we try to tinker with its trim profile, plug profile, and see how it impacts the flow characteristics. So we'll end with one real life success story from our through our client, and we'll end the session with Q&A things. So meanwhile, like we are going to have a detailed question and answer session at the end. But anytime you feel like you have some questions you want to post it, please use the chat window to post it. We'll compile and submit up, and we'll address those queries at the end. So I would like to, before we start with the understanding of what is valve CV, but I want to, present a few facts. It's like a food for thought kind of thing. So imagine just, I just pulled out a kind of a news or fact from some article. So it says a major offshore oil and gas facility somewhere located, it has a problem. It experiences a frequent problem by its, experienced by its second stage water transfer pumps. So on a closer inspection, what they found was the valve which was supposed to, the system requires a 310 meter cube per hour flow, but the valve was designed to handle a maximum flow of 257. So clearly, it's an undersized valve problem. And the undersized valve is experiencing a higher pressure drop, and then the restriction, the pressure buildups in the system, and then the valve, there is a risk involved. It can damage the upstream pump and other equipments in the line. So just take a minute and see, what would have caused this undersized valve in first place. Either the sizing calculations might have gone wrong, or the data provided by the manufacturer has some, inaccuracies or anything. So it could be the reason. There could be other reasons also, the installation and other parts. But majorly there is some data mismatch between what was promised and what is given. So that can be a good, a possible reason. And then this will cause unexpected, unscheduled downtime and replacement cost and everything, whatnot, right? So I'll quote another fact from recent article from Valve World. So which says accuracy is money when it comes to high stakes of custody transfer. So accuracy is very essential in custody transfer, where fluids or gases are exchanged between parties on precise calculation. So even a small error can cause significant financial loss. So here they presented an example of some pump station where they transfer kind of 60,000 gallons of oil flow per minute, and then a small 0.1 percentage error calculation goes to daily discrepancy of around 2000 barrels, which the cost comes to on a daily loss of this much. So it's a huge loss. So accuracy and money. Although the context of this article was more on the side of on-field flow meter measurements accuracy, still the device, the valve design and its accuracy of CV has a role in in this kind of cases. So accuracy is money. So with this context, let's enter into today's topic. So we have a wide set of audience joined today. So some might be familiar with valve terminologies and things. Some might not. So I'll start with this and to cover to bring everyone on the same page. So what is valve? So valves are some some devices that changes the flow area, restrict the flow area to bring control over flow or pressure, fluid level, or temperature. So it does this by varying the flow area. So the pressure goes down, velocity goes up, and the area changes as the area changes. So the same concept, there are different types of valves, majorly grouped into, rotating and linear motion valves based on the motion they undergo to, regulate the flow. And on another type is majorly isolation and control. So whether it is a on-off or more control valves. So the types range from ball valve, butterfly valve, plug. So these falls under the rotating valve category, and then the globe valve, diaphragm valve, pinch valve. So these fall under the linear motion type. So there, the valves are application area of valves are you pick any domain or any vertical, you will find valves application there, starting from oil and gas, upstream, midstream, downstream, and then dairy products, power generation, everywhere you will find valve applications. So we'll introduce valve flow coefficient CV. So valves are provided manufactured by different manufacturers, and they come in different sizes as well. How do you compare something and then choose a right valve size for your flow requirements, right? So there is a index or flow performance coefficient, which is CV. It describes the flow capacity per unit pressure drop. So this defines what is the flow capacity of a particular valve, of particular valve design and size. Okay. So for every angle of opening or percentage of opening, the CV or flow capacity varies. So the valve manufacturers are supposed to provide this data sheet with the percentage of opening and the CV values. So moving ahead, the official definition given is the volume of water at 60 degree Fahrenheit that will flow through valve per minute with a pressure drop of 1 psi across the valve. So a typical CV curve looks like this, and for every opening, the CV value or data is calculated based on the amount of flow with respect to the pressure drop across the valve. Okay. So, what is the importance of CV? Although at the start of the slides, like session, we pulled out some facts to look at what is the importance of CV. Okay, what happens when the CV is not rightly done or rightly published, or a valve is undersized or oversized? So it can cause big losses and damage to the system and the service life and everything, associated problems. So it helps in comparing different valves and compare their flow capacity, select the right size of the valve for your job, and also let you know the CV curves, let you know what is the flow characteristics of the valve. So depending on the design of the trim or a plug, it might behave like a quick opening valve and are a linear one or an equal percentage one. So when I say quick opening, say it's for some application where there is a large amount of water or flow is required to immediately shut off something or cool down something in some nuclear application something. So their quick opening might be useful. So where different application, it has its own application, quick opening, linear, and equal percentage. So CV curve lets you know what is the flow characteristics of the valve. So moving ahead, how to measure the valve coefficient flow loop testing. So flow loop testing happens in certified laboratories across the countries. So for example, UWRL in Utah and Utah Laboratories, Water Research Laboratories, and Fluid Control Research in laboratories in India, Kerala. So they follow standards like ANSI ISA 75.42.01. These standards specify how to conduct this flow loop test to extract flow capacity or CV. So where to install the probes. So for example, on the upstream side, the pressure measurement probe should be at 2D before the test specimen and then 6D in the downstream side, so outlet side. So the pressure drop is measured between these two probes. So what happens in a new product development is a design requirement comes and they have a target CV based on the competitors or the actual requirement of the job, okay, custom requirement. So they have a design target. This is the flow capacity we need to achieve through this design. So the design engineer, using his previous skills and past experiences, designs the valve and it is manufactured. The prototype of the design is manufactured and it is transported to some remote facility, it's like to the flow loop test facility. And then the flow loop test facility provides you with the report, which has the CV and CDT if it is a rotary valve. So all these flow report tests and just the whole cycle, including it doesn't. If I exclude the manufacturing time and prototype manufacturing and transport, so the results will take weeks, multiple weeks, sometimes more than months. It goes in queue and then it takes months time. So imagine what if the CV is not met, the target CV is not achieved, then you have a big problem. Again, you have to go through, do some design modification, go through the same cycle, and it again involves more cost and time. Okay? So, what are the challenges? Another challenge is limited flow insights. What you get from the flow loop test facility is the report, which has a CV value, but it doesn't tell you what went wrong with the first design or the baseline design, where you need to do the changes, how to improve your design. So based on just your past experience, and then you make a guesswork and do some changes. So that is a limiting factor, limiting factor. What went wrong? So those flow insights where there are flow separation, where there is more, pressure drop happened. How can I improve the CV? So that information is missing. Then comes the design changes. So any design changes you do, it has to go through the whole cycle. So cost and time factor involved. And then in some cases where your valve size is very large, then it is limited. Test facility has a limitation to test, how much is the valve size that can be tested. So there are other alternate methods, analytical and numerical. Numerical method, also called as CFD, computational fluid dynamics. So we'll see all those in few slides. So analytical method and numerical method has its own benefits and pros and cons. So the accuracy part, the time and cost, skill required for analytical methods very simple, but the accuracy is compromised. At the same time, when you go for conventional CFD process, the accuracy is much better, very close to flow loop, but the time, cost, and the skill required is higher. So we'll see one by one. So in analytical method, as discussed, the accuracy part is a big challenge. Complex flow phenomena like turbulence, swirl, and separation specific to your design that may not be accounted in the empirical formulas. Okay, that needs to be adjusted. So there is a compromise in that case. So coming to computational fluid dynamics, that is nothing but it's a science of predicting fluid flow and heat transfer and other associated flow physics using numerical methods solved in a computer. So your flow domain where the fluid flows is discretized into these kind of shapes, what is called mesh, and then numerical equations or governing equations are solved in numerical form in a discretized form in this elements, mesh elements. So I'm just explaining it in a layman term. So I don't want to burden you with CFD jargons and things. So this you can take it like a CFD is another method which needs more skills and processes to achieve the results. So the benefit of CFD is it provides more flow insights. So you will get the complete pressure data or velocity data in through and throughout the flow domain. So addition to the report or CV curve, which we get from flow loop test, we also get more insights to it. So where the velocity is maximum, where the pressure is minimum, that is prone to cavitation, where the flow separation happens or recirculation happens, that is a scope to improve the design and reduce the energy consumption. Kind of pressure loss can be minimized. So those kind of flow insights we can achieve. So a conventional CFD approach goes through, it starts from CAD model, geometry 3D CAD model, and we extract the fluid domain and we do some CAD cleanup and then generate some meshing and then do some boundary conditions and turbulence model, numerical methods, everything, and set up the problem and solve using computers. So it requires high performance computers to solve the CFD problems. And then the results provide colorful results. So each color indicates a range of data. Okay, and then we get the graphs more both qualitative and quantitative data. The problem here is it's very manual intense process and it requires high expertise skill sets required. So that is one challenge. So if you give the same problem and same software, same design to two different people with different experience, one is novice, like entry level engineer in CFD, and the other one is expert. Both there is a chance that both can give you two different CV values. Okay? So it all depends on the many conditions and the CFD experience and expertise. So that is a big challenge here. And it is to solve the CFD problem or simulation, to perform the CFD simulation, it demands a high performance computing in house. And then it comes with a software licensing cost and annual maintenance cost and whatnot, desktop software. So here comes autonomous valve CFD. So we thought, what if we make address all those challenges, make the all the CFD process autonomous, meaning the design engineer doesn't need to know CFD intricacies per se, but he should be able to, start with the CAD model and get the CFD results. And what if there is no need of in-house or desktop, in-house high performance computers? The simulations runs on the cloud, right? So all to addressing all these things, so we develop this software or app, which is Autonomous Valve CFD. So it's nothing but a virtual flow loop testing tool. So which mimics closely the actual flow loop test. It follows all the conditions mentioned in the standards, like ISA, ANSI ISA, and M49 manual for cavitation and torque related calculations. So it provides it provides the CV, KV, CDT, the torque coefficient and cavitation index. We'll talk about torque coefficient and cavitation index in the further next week sessions. And it is powered by our Autodesk platform services to view the CAD model and view the results on the browser, post-processing results on the browser. And then it utilizes, it leverages AWS, Amazon Web Services for the cloud computing. And OpenFOAM is the backend solver and backed by simulation of API service. So to simply put, what happens is it requires the app requires three set of inputs. One is the valve CAD model and the flow direction, whether it is a flow to open or flow to close or shaft upstream or shaft downstream kind of flow direction. And you specify the opening conditions for which you want to simulate, for which you want to evaluate the flow performance. Okay, so simple. So these three inputs are fed to the app, and the app does all the CFD processes autonomously in the backend, and then provides you with these multiple results. So velocity, flow lines, pressure drop, contours, and then the quantitative results, which is very critical. So CV data, CV curve, CDT curve, head loss coefficient, cavitation index, all those tables and graphs are provided, and everything compiled in a nice report, which is kind of, you can ready to hand it over to the end client or the analysis, use it for the analysis. So it's that simple. Okay. So this app supports all this type of valves. So control valves, isolation valves, all the rotary and linear motion type. And we'll see a demonstration of the app, how simple it is, how to extract the CV values and what goes in and what comes out from here. Akshay will take over from here. Akshay, over to you.
Thank you, Praveen. That was an excellent introduction to our today's topic about the flow coefficient CV, how it impacts the real world scenarios and how we can extract this value from our application ABC. So we'll just quickly dive.
Would you like to share your screen?
Yes, I'm sharing my screen.
Oh, okay.
Is my screen visible?
Yes, yes, yes. Still it is in slide mode, yeah. You can go to the demo slide. Yeah.
So sorry for that.
You're
Yes,
welcome.
let's just look at the quick demo of ABC. So this is the dashboard of the application. We just give it a quick name, a brief description of your simulation. We'll just hit the create simulation button. Yeah, we'll upload a file here. So you can support all sorts of CAD files, CAD neutral files, CAD specific files are supported by ABC. Just quickly choose the valve type, valve size, pipe schedule, pressure class, roughness values. We'll move on to the next part, which is the moving part selection. So we just adjust our view. We'll select the moving parts and we'll select this axis of rotation. Just give the rated opening. It's a quarter ton wall, so we'll input 90 degree. We'll provide how many angles we want. What are the steps? We'll just preview the direction. In case there's a stopper in your valve, you can also reverse the direction. Moving on to the next stage. We'll just define the flow direction. So we just select the inlet and outlet pipes. Very simple, very intuitive UI. And the last part is submitting the simulation. That's it. So as a design engineer who has no CFD background can easily upload their designs and run their first CFD simulation within a couple of minutes or maybe 5 minutes. That's it. Now the autonomous workflow takes over. It generates the fluid volume, the mesh, it solves the CFD simulation, it generates the post-processing results, and all of this can be viewed in the APS viewer of the application. So you get the quantitative data, which is the CV, KV, head loss coefficient, CDT. You get it in tabular form, you get it in graphical format. So let's say you want to export this, you can export this in CSV format, you can export this in as an image. You can also view the streamlines in the post-processing view of the application. This is like a very awesome marketing content to showcase your walls for your end users. And this is where you can actually get the insights from the CFD simulation. You can view the contours, you can view the velocity, you can see where it's accelerating, where it's stalling, where there's a high pressure zone, where there's a low pressure zone. So it actually gives the designers the power to extract insights from their wall design. At the end, you have a consolidated report, which gives all the details that we just looked. So tables, graphs, it will give you a brief introduction of the CFD methodology. It will give you the formulas that are used for calculating the CV. It will give you a section view of the contours, pressure, velocity, in a consolidated format. So that was a quick overview of the application. So moving ahead, we will go into a case study that we just did to understand, really understand and feel how the trim design can impact the flow characteristics of a valve. So let's move ahead. These are the inputs that AVC requires. So from a designer's point of view, you just need a CAD file. Again, any CAD neutral format, CAD specific format like step file, IPT file, parasolid file, that's no problem. The app can handle it. You select the moving parts, you select the flow direction. What the app does autonomously is completely autonomously, you can say it's a autonomous workflow. It automates the entire CFD workflow for you. So it does the CAD cleanup and fluid volume extraction. Then it generates the mesh. It submits the simulation on cloud service to, get the CFD results in like say 30 minutes. And the output is in three formats. You get the actual CFD 3D results, which you can actually view in the application in terms of flow lines, in terms of contours, in terms of surface pressures. And you also get quantitative data in the tabular and in the graphical format, and a consolidated report for the CFD simulation. So it contains your quantitative data and your qualitative data. So to actually understand the impact of trim design on flow characteristics, we, as as curious CFD engineers, we just went through some quick Google search, and from some quick, like reading through some references, we just designed three different, you can say, plug designs for a globe valve. And we actually wanted to see how, see the trim design will impact the flow characteristic. So we selected one profile, modified it a bit, and then modified it further. So three designs, and this is the result that we got. So the profile here, the first profile that we have, you know, uh, in the initial openings, it has a lot of flow rate going through it. The second one, it's somewhat of a, you can say, linear profile. And from the analysis, we found that the third profile is somewhat of a, you can say, a equal percentage profile. So again, don't judge us on the profile design. It's just a very basic reading and references. We just wanted to see the impact, but we actually see that impact. So even a small change in the trim design from profile 2 to profile 1 to profile 2 has a huge impact on the characteristic of the valve. So to have a comparative analysis, what we have done is we have scaled everything in a percentage CV format. So what we did was extracted the CV, took the maximum value of the CV for each opening, and converted it in percentage so that we can have a comparative analysis for all the three designs. So your CV goes from 0 to 100, your opening goes from 0 to 100, and it gives you a very insightful understanding into how these profiles basically, have encoded that characteristic in their profiles. So what's the use of, like, we'll see this in terms of CFD. So we took the CAD, we saw the impact in a graphical format, but why that happens is the, you can say, the power of CFD. So we just took an opening where we saw that there is a huge difference in the characteristic of the three profiles, and we analyzed them using our application. And what we found out is in the actual, so the profile number 1, which is depicted by the blue curve, the area of opening for the flow is 3.8 centimeters square. So the flow rate is more, it's around 10. Similarly, for profile number 1, we saw that for the same travel, so this is the valve opening, which is the travel of the plug. For the same travel, the opening area was less, so the flow rate was less and the CV was less. Moving on to the next profile, profile number 2, same travel, lesser area, lesser flow rate. And you can also see how the flow accelerates through these small openings and how it can impact your valve performance. So we have seen the impact of CV, but which CV is this? So I would like to give you a disclaimer. This is the inherent characteristic of the valve. So once installed in a process or in a system, the inherent characteristics of the valve might change due to the additional losses, due to pipe bends, due to additional fittings. So AVC application gives you the inherent characteristics of the valve. Let's say you want the installed characteristics. So we would have to do, let's say, a 1D simulation or add few parameters, and that can be extracted. But the main, you can say, the essential pressure drop or the essential characteristic of even the installed characteristics is governed by the valve. So this is all great. CFD is working, AVC is working, but how is it working? How exactly does AVC or the CFD software able to do this? I would like Praveen Kumar to explain this bit further.
Yes, yes. Thanks, Akshay. That's a wonderful demonstration and walk through the case study. So it's an interesting case study. So what makes it more interesting is the whole simulation and results analysis. Everything happened in kind of 1 to 2 hours time duration. So once we have all three designs, so it took us 1 to 1.5 hours of time. So how is that possible? To understand that, we need to see what happens behind the scenes. So you know, I would say, rather than calling it behind the scenes, what happens up in the cloud. So what happens in the cloud, right? So let's see that. So when we have upload a CAD model to the AVC app and provide certain inputs. So let's say we are running for the maximum opening. Okay. So what happens is for that one opening, it assigns the app assigns a 36 core Amazon EC2 instance machine, and it does all the CFD processes autonomously using the simulation of APIs, cat cleanup, meshing, monitoring the solve convergence, doing the setup, CFD setup, boundary conditions, everything. So and then it gives back the like simulation results. So which is CV, it calculates CV, and then you are able to see. So this is one data point. Now imagine you doing the same thing for multiple openings. So from fully closed to fully open, something like that. So what happens is for every opening percentage, the same process happens, and a dedicated machine is assigned for every opening. So you can imagine obtaining all this process and everything happen parallel. It's not sequential. It's unlike the desktop software where it is node log license limited by the licenses. So one opening simulation, other openings has to wait till one app opening completes, the simulation completes. And then you can see here, so because the runs happen parallelly, all these simulation results are available at the end of 1 hour. Okay. So what you get is a CV curve and the quantitative as well as qualitative results and the report. So what Akshay did here is he took three designs, and he had three designs at the same time at the initial time. So he did the simulation. He started the simulation for all three designs from the same account, same login, and there is no limitations on licenses per se. The same user can run multiple design iterations at the same time. So the same process happens for all three design options, the profile designs he had. And then we obtained the CV curve, different CV curves for the design at the end, and he had to compare. So this is the power of the cloud and autonomous thing. So it's a seamless collaboration across different teams. You can extend the same thing. Let's say your team sits from different locations, and then they work on different lines. One working on different product line, like one ball valve, globe valve. Everything can be done at the same time, simulated at the same time. So there is no restrictions or anything. And here is a small comparison between a conventional method. What if Akshay would have taken, a conventional approach? So he has to, depend on a simulation expert. He himself, in this case, he himself is a simulation expert. But still, so he has to depend on a simulation expert who does all the process manually, the CAD cleaner, fluid volume extraction machine, solver, everything manually, and then rely on the limited in-house computational resources. And then the results, it takes typically weeks of time to obtain the complete CV curve. And in this case, he had three CV curves to extract. So three designs to be evaluated. So it easily takes more than 3 weeks or like 2 to 3 weeks of time. So on the same contrary, like he used simulation of CFD, autonomous CFD solution, and the process happened autonomous, and cloud compute expands, depending on the number of opening or the number of designs, each, the number of machines assigned for him, for his account, it expands, and at the end of simulation, it takes 1 to 2 hours, and then you get the results. So this is the quick comparison. So always I used to take this analogy or metaphor. So let's say you want to plant a sapling in your garden. You want to dig a small pit. So what do you do? Which tool would you choose? Would you choose a bulldozer or kind of JCB thing, or would you take gardening tools? So I would compare this JCB or thing with a conventional generic CFD tools, which using which you can do simulation of a small pipe as well as a large aerospace or complex simulations. So there are all sort of options, the turbulence models and everything is thrown at the face of engineer. So whereas these design tools are specifically for this particular job, only specified to valves. So valve flow simulation. So that's a small, a casual on a lighter note comparison. And then with the process, you can ask like Praveen, the process is completely autonomous, and with great powers comes great responsibility. What about the accuracy of results? So we understand this, and we have validated the process and the results with multiple number of lab data. So, for example, we have conducted more than 50 plus comparison study, validation study with lab data from FCRI and Utah Water Research Laboratories. So it covers a wide range of sizes and different types of valves. So all sort of CV or diameters as well as types, valve types are covered. And what we observed is we consistently fall in the range of plus or minus 5% error, okay, which is pretty good in CFD terms. So the case study which Akshay presented was a hypothetical one, which we kind of curious engineers, we tried some tinkering with the plug profile and see how good it is, kind of. So I'll present you a real success story with our clients. So these are the current customers of Autonomous Valve CFD application, so across the globe. And I'll present one case study of Bray. Bray International is a biggest valve manufacturer in North America. It has offices in many places and design centers in Houston, Bangalore, and many locations. And the challenges they were facing before we entered was, the flow loop test they conduct it used to take, including the prototype manufacturing and things. So it easily takes, 3 months of time for every valve design. So they already had a CFD team and generic CFD tools, but again, it was limited by the number of licenses and the in-house CFD experts, number of experts they had. So they were overworked, and the backlog was huge. So the designs are waiting in line for simulation. So it easily takes up to 2 weeks of waiting time, and then on top of it, 5 days to extract a single CV curve for a single design. So these were becoming a big bottleneck for them. That's where we entered. So we provided autonomous valve CFD solution. So using which they had reduced their 5 days of simulation time to 1 to 2 hours, and that helped them to increase the number of valves they test or simulate. So more than we have been associated with them for past 6 years. They have been our premium enterprise customer from 2019 and continuing. So around 1200 plus valves have been designed, verified, or simulated using our app. And initially, they started with 3 design engineers using this application. Or now the number has increased up to 30 users because they find it very easy and quick to use the app and extract the do the CFD simulation. So now the CFD experts are free for doing much complex simulations like noise and other stuff in the valve. erosion and noise. And whereas simple, straightforward CV simulations, I'm using the word simple because we made it simple. Yeah. So those things are handled by the design engineers themselves. So the cost benefit of autonomous valve CFD is very large, and also not to forget, the flow loop tests uh, adds to carbon footprint, and we have saved a lot of waters and tons of CO2. So that's the success story of Bray, and our partnership with Bray goes long way, as I said. So we can often, to our customers, we often visit them, interact with their team, understand their, pain points or any custom requirements they have. So we keep improving the product to suit their requirement and to address their concerns. So yeah, we also conduct regular trainings and everything for the team. And this is some kind words from the man himself, Brindesh Dhruva, so CMO and CTO of Bray. Uh, yeah. So he himself like says how it helped, how AVC helped in accurate prediction of CV and other flow parameters, and how it reduced the need of expensive physical prototyping and testing. So the design iterations are done in the CFD app, and only the final design goes to the physical load test. Yeah. So what's next from here? So there is a trial subscription plan available for a typical, any visitor. So the trial subscription is 15 days, and we provide 20 simulation credits in the trial period. So you get to simulate 20 valve openings, and what you can do is um we can schedule. You can connect with us, contact us, and schedule a call with our expert. And for our webinar series registered attendees, we will provide exclusive 1 month instead of 15 days, and more simulation credits, and some exclusive discount in subscription. Okay, subscription. So that's it. So you can connect back to, you can write to us, and we'll arrange a call, and we'll hear you what is your requirement, and provide a custom solution to it. So we are towards the end of this. We can start with the Q&A session. So you can post your questions. I see some questions in the chat. Just give me a minute.
So Praveen, here's a
Is it
question.
possible? Yeah, yes, yes.
Yeah, I guess Hari has asked this question. Which 3D format is suitable?
For
So,
formats or
I think he's referring to the AVC software itself. So, Hari, I think we support almost all the CAD neutral formats. So, step format, IPT format, parasolid format are supported by the application. Uh, let's say in case you want a custom, you're using some specific CAD tool and it might not have support in our app, we can integrate that as well. So even that is possible. But the standard step parasolid formats are readily available and usable in the application.
okay. So there is another question by Hari, I guess. So is it possible to run a 20-inch valve with 10,000 holes in cages, in which diameter of the hole is 1.6 mm in just 5 minutes? In just 5 minutes, okay. Just 5 minutes is kind of, that's not possible. Okay. What we said, what Akshay mentioned was to start the setup. It takes 5 minutes to 10 minutes. Once the simulation starts, depending on the complexity and the number of cloud computing machines, the solution varies. So, but because this is a good question, so I'll just let me quickly pull some slides. Um, yeah, okay. So what we have added is some more new features, which brings more mesh refinement to support complex anti-cavitation trim designs. So with lot of holes and of any sizes, so you can keep on refining, and that can be done. So that supports, even very complex shapes and to support all the additive manufactured valve trims. So you can see here. So all these things are possible, but not in 5 minutes. Maybe it takes 2 to 4 hours depending on the complexity. But it completes the complete opening for all the openings. It takes the same time, and by the end of 4 hours, you'll get the complete CV curve and every detail for the fully closed to fully open. Okay? So that's the realistic timeline, I would say. Yeah. So going back to the questions.
Praveen,
Yes,
Joel
yes.
has asked a question. How does
Yeah.
the software automatically set more refined mesh in the regions where it's required? Or is it
Oh, okay.
uniform mesh throughout? If that's the case, wouldn't there be a compromise on either the competition time or accuracy?
Okay. That's a good question. Let me see. Yeah, yeah, yeah. Okay, so what happens is the algorithm detects it considers two parameters. One is the geometrical gradient and also the flow related refinement. It does both the things. So it's not a uniform mesh. So it's a proper CFD mesh, as if an experienced CFD engineer would do some grid independent study and completely with prism layers and everything. So you can see the mesh is a bit coarse, and then it goes to next level of refinement, and near the surfaces there is another level of refinement, and near the edges it automatically detects the edges and it goes to a additional refinement. Okay, and on top of it there are prism layers to capture the boundary layer physics, so flow separation and the velocity profile. So all those things are, and on top of it, for whom uh, uh, based on the nature of question, I'm extending the answer. So for CFD engineers who has worked made their hands dirty in making the mesh and improving the quality, so they understand how much time goes into this cat cleanup and things. So what happens is the app automatically checks for the non-ortho faces, skew faces, and wrong oriented faces, and if there are any errors, it does the repairing work and does the refinement in those local region, and again goes for the check mesh unless it passes. Okay, so this is it, and even the other processes like the residual convergence and monitoring of pressure and CV monitor, everything is done by the autonomous algorithm. So it uses both automation plus the AI to predict the convergence and monitor the convergence and things. Yeah, I think I've answered the question.
Uh, yes. Thank you, Praveen. One question from Arjun. How
Okay.
close are the CV values to the real life flow tests?
Yeah, so that's what we showed in this validation study. So where we compared, so these results are compared with multiple lab tested data, and we observed around 90% accuracy. When I say 90%, it's kind of plus or minus 5%. That's the range. And on top of these already done studies, if you have any of your case or validation sorry the lab tested data, so we are open to conduct a validation study to start with, to gain your trust and things, and then we can proceed with the subscription or yes. Okay, so any other questions? So let me check. Let me check. Let me check. Okay, that has been answered. This is answered. Uh, yes, I guess that's it. So we are near the end of the session. Uh, and moving forward, next week, Wednesday, please, again, come back, show up, and we'll provide you with some more interesting case studies in terms of quarter turn valves and CDT torque related discussions will be there. And then further, in the third week, we'll have cavitation related stuff. And we'll also present some research study which we conducted and presented in Valve World Conference in Germany. So that research study also will provide. So how do we calculate liquid pressure recovery factor? So FL. So stay tuned and see you on next Wednesday. But meanwhile, if you feel like you have some thing to share or ask, so write us to on support@simulationhub.com or visit our website. You can um, yeah.
Uh,
So
Praveen, just before
yeah,
dropping off,
yes,
if we can take one last question.
sure. We have 4 minutes more. Yes, yes.
Great, great, great. So Joel has asked again a CFD aligned question for you.
Okay,
So the software ensures that the Y plus falls within range to ensure accuracy, even if the convergence with low accuracy, even
okay.
if the results converges with low accuracy.
Okay. So there is like I explained in the meshing part, right? So if there is a quality check, there is a quality check that checks, what is the quality of mesh, and then it improves. Similarly, what we have implemented is a Y plus checker. So what it does is it checks once the result is achieved. So it checks for the percentage of surface area or cells which satisfies the Y plus criteria based on the turbulence model. So once it satisfies that criteria of some more than 70%, 80% of the cells or the near first cell falls in the demand or required Y plus range, then it goes to the pass criterion. Otherwise, it does the changes in the mesh, and then it coarsen it or refine it depending on the Y plus, and then it changes the turbulence models also. For some cases, you cannot have a you cannot achieve the complete Y plus demand. So what it does is it changes the model and applies the appropriate thing. So all these have been trained in the past. So for different valve sizes, what setting needs to be done. So everything is decided based on the training data by the app itself. Thanks for this question. Okay, so you can contact us and schedule a demo call with us, and we'll happy to connect and interact. Thanks for joining. Have a wonderful day and good night for Indian people who are joined. Okay. Thank you.
Thank
Thanks,
you.
Akshay. Thanks for your
Thanks, Praveen, for this wonderful webinar.